saying. Thank you very much.
Thank you very much for this very nice introduction. Good afternoon, ladies and gentlemen. Indeed, if you have thought that echocardiography or the development of echocardiography is at its end, then you might be wrong, and I would like to take you on a little journey, or I want to have a look in a crystal ball together with you, what the future of echocardiography might bring for us as clinicians. You might remember from your very early lectures how echo imaging works, because that is sending out an ultrasound impulse, and that impulse travels through the tissue, is reflected and returns to the probe, and that all takes time. We know how fast the sound travels in tissue, and we have a certain anatomical arrangement which we cannot change. So like a round trip is about 30 centimeters, going 15 centimeters down and back. So that takes us 200 microseconds for an echo impulse to return to the probe, and that allows us, in other words, to send maximum 5,000 impulses per second. And now we can determine what to do with those impulses. Usually what we do, we use one impulse to send it out in a certain direction to make a scan line out of it. And then we have like 180 scan lines per image. So in other words, we need around 36 microseconds for building up one frame, which leaves us with 28 frames per second. For cardiology purposes, this is on the edge. That's nowadays, I would say, regarded as too low already. So what can we do? Because this is physics. How can we increase frame rate? Well, what is done nowadays is a little trick. So you can focus your ultrasound on the sending side, sending it in a certain direction, but you can also focus your listening. You can listen in a certain direction. And this is used nowadays by making the ultrasound impulse a little bit broader. So you're sending a bit or less sharp in a certain direction, and you focus very sharp only on receive. And in that way, you can hear two lines while sending only one pulse. And in that way, you can double your frequency from 28 frames per second with one sending impulse, one receiving, to, let's say, 56 frames per second. And this is what you know all from your echo machines. That's standard nowadays. But theoretically, you could push that principle further. You could think about using one pulse for generating an entire image. So you send the pulse completely unfocused in all directions of the sector, and you listen only in a certain direction on receive, and in that way you could theoretically use all the 5,000 pulses for making an image, so we end up at 5,000 frames per second. That sounds a lot. It is a lot. It's nothing that can be handled by commercial machines, so you need some engineers to build some box for you to play with these things. It's also a huge amount of data. We have like a DVD of data for a heartbeat, which needs also some time for post-processing. And the image quality is also not as good as you're used to it, because you have to imagine that the energy which is usually needed for one line is now used for an entire image, so the signal-to-noise ratio is also a bit worse. And that's why we usually compound images. You see here a typical image on the right side, where we have 5,260 frames per second, and then we compound 2 or 3 frames or sometimes more to get a little bit better signal-to-noise ratio, and this is what we are working with at the moment. So the question is, of course, why do we need that? Why do we need 5,000 or thousands of frames per second? One thing, and that might be an interesting application, is that we can use it for blood flow imaging, because blood flows rather quickly, so we have to be fast with that. Maybe not 5,000, but in the range of several hundred to 1,000 frames per second. And then we can use the image data to do speckle tracking on the erythrocyte echoes. And that can be done without any contrast, so it's a big advancement compared to these previous methods that used contrast and normal flow imaging, normal echocardiographic imaging, which was way too slow for resolving the flow velocities. And this is here data from Trondheim, from Norway, from a research group that's working on that, taken with 8,000 frames per second, some temporal filtering. And then they can show Doppler-like images, but they can also show on top of that streamlines, so they can really show you where the blood is going to. And that has been validated, that it works reasonably well. It needs good image quality, so neonates, small children are the ideal population to do such imaging. And here you see fetal imaging and the gestational week 24, where you see flow inside the cardiac chambers, and here you can see flow inside the aorta. And maybe that can be used also for early diagnosis making, like in this case, where you can clearly see the shunt in the interventricular septum here, where the blood is going from the left to the right ventricle. Another group which is dealing with these things works in Paris, and this group has worked on myocardial blood flow imaging, even in 3D with high frame rate, and these are magicians of high frame rate imaging there in Paris. And these guys have looked into the blood flow here of the myocardium. What you see here is the myocardial wall magnified. That's the epicardium, that's the cavity. And these blue lines here are the intramyocardial blood vessels, and you see in systole and diastole that they change the color from blue to red, and they can even go so far that they can measure the blood flow in a single capillary inside the myocardial tissue. That's close to magic. What you could also do is something else. This is shear wave imaging. Shear wave imaging might be also something very interesting, and I would like to start with explaining shortly what shear waves are. Shear waves are oscillations that are transverse to a propagation direction. So like if you drop a stone in the water, you have this rippling of the water which propagates to the side, and that is typically what a shear wave is. And you can have such shear waves also in the myocardium. You could imagine to excite such a shear wave with a strong ultrasound impulse, which is pushing the myocardium a little bit, and then you have a shivering of the myocardium that travels along the tissue. Or you can also excite such a shear wave internally, for example, by aortic valve closure. This closure of the valve, this clap, also generates a little shivering that travels then from the base to the apex of the myocardium. Again, why should we do all this? Well, we can image that with high frame rate imaging. We can measure the propagation velocity of these shear waves, and the interesting thing there is that if we can measure that, we can say something about, that looks a bit complicated now, but this E is nothing else than myocardial stiffness. And that's a very interesting parameter. We can say, for example, something about diastolic function, or we can say something about active stiffness, which would be very close to contractility. And that has been tried. This is an animal experiment from the Paris group, and they have done that with push pulses. So they excite the shear waves with an ultrasound, with a strong ultrasound impulse on the myocardium. That's an open chest PIC model, and you see here the stiffness change during the cardiac cycle. This is our research group, or some of our people, mainly the engineers, looking very excited at the screen, but they're also having fun with their work. And this is the ultra-high frame rate scanner, which they built. And what we do, we use the naturally occurring shear waves, so those that are excited by the mitral valve and aortic valve closure. And what I show you here is a color M mode along the septum, and the color coding shows us the acceleration of the tissue. And if we draw an M mode line through the septum, then we can see very nicely this wave that travels from the base to the apex. And the steepness of that slope tells us something about the propagation velocity, and with this, something about the stiffness of the tissue. We have validated that in a model. This is just an agar-gel model with some graphite in it to have some reflectors, and we dropped a steel ball on it to excite a shear wave and measure that with our equipment. That was done in 2 states, in a normal state and a frozen state, to make it harder. And you see here the expected values in green and the measured values in blue, so that fits very well. Theory and practice comes very close together with a very little error. And then we started to use that in the clinic, or not to use it, but to try it out in the clinic. To show you a few examples, this is data from Canada, from Toronto, where shear wave imaging was tried in a pediatric population as pilot experiment, also with a push pulse that can be done in children, because the image quality is usually excellent. This is from the Paris team looking into the stiffness of the myocardium in normal volunteers over age, and they showed a very nice dependence of myocardial diastolic stiffness over with increasing age. This is something which we always suspected, but we have never seen such nice data on that. And then they also looked into hypertrophic cardiomyopathies. And these measurements are far away from what you find in normal, so that gives also some confidence that this is a measurement which is not changing by a few percent only if you come from normality to disease, but this is something which is really completely different in pathology. This is our setup in Leuven. We still need 2 people for doing the imaging, so we have a doctor who is doing the echo, and we have an engineer for running the high frame rate machine, and then we have a normal echo machine next to it for taking the standard echo views. And we built these M modes, as I showed you, and usually we find these shear waves at mitral valve closure and at aortic valve closure and can measure them. We have looked into volunteers and into patients with cardiac amyloidosis, which is also a condition where the myocardium gets stiffer. And in the volunteers, we could also confirm that there is an increase in stiffness of the myocardium with increasing age, both at the mitral valve closure, but also at the aortic valve closure. And we could show that there is a clear difference in the stiffness of the myocardium when you compare controls and patients with an amyloidosis. And when you compare the stiffness measurements with the diastolic dysfunction degree, then also here you see a very nice correlation of the data. Here is a correlation with the E over E prime and the mitral valve closure shear wave velocity. What might be also interesting in the context here is that we looked into myocardial stiffness of transplant recipients. There we studied almost 50 patients with our echocardiographic elastography, but they also got a right heart catheterization, which is nowadays the gold standard method for determining the state of the myocardium. And we also had in most of them cardiac MRI T1 mapping, which tells us something about diffuse fibrosis of the hearts. And what was very nice to see is that the wedge pressure measurement from the right heart catheterization correlated with the T1, so with a fibrosis measurement from the MRI. This correlation was reasonable, but it was not really exciting. What was really exciting for me is that the shear wave velocity, so the stiffness measurement, correlated very, very nicely with the T1 measurement. Theoretically, you could also think of systolic measurements. Then you could maybe say something about systolic function, about contractility of the myocardium. There we are in an experimental stage still. I can just show you some initial results where we have looked into the changes in shear wave velocities with dobutamine. So you see a clear increase in the steepness of that slope, and that happens not only in the dobutamine stress echo, but that happens also with bicycle stress. Here you see the correlation between the different challenges and the end-systolic elastance, which is close to the contractility. Ladies and gentlemen, I think that the concept of high frame rate echocardiography is technically feasible. In theory, only depending on image depth, we can achieve frame rates in the range of 5,000 frames per second or more. We can use that for different applications. We can do tracking of the blood flow, for example, like tracking erythrocytes, or we can use it for shear wave imaging, which is a very interesting new way of determining or characterizing myocardial properties. And of course, there are still a lot of issues to solve. It's a very bad signal-to-noise ratio. We have to see that we get good signals if we scan very deep. We do not know exactly how these shear waves travel through the myocardium in different directions. If there is any interaction with wall thickness, in theory not, but practically probably yes. So all these things still need to be explored. This is an experimental stage, but we are working on that with great pleasure and with a lot of people. This is our engineering team and the doctors from our medical imaging research lab in Leuven. And in case you got interested in these things, I just want to say that we have a meeting in February in Leuven where you will hear the latest news about the development in this technique. Thank you very much.